Good morning, good afternoon, good evening, everybody, and thanks for joining this session titled A Gentle Introduction to Containers and Kubernetes. My name is Nils. I'm a cloud solution architect with Microsoft, and I'll be guiding you through this session today. For those of you in the software industry, you might have noticed that containers and Kubernetes are gaining a lot of traction, a lot of attention, and luckily enough, a lot of adoption as well. And the goal of this session is to help you understand the what, the why, and the how behind both containers and Kubernetes on Azure. And if my slides want to progress with me, sorry for this technical difficulty. Cool, here we are. So the goal for this session, as I said, is to understand the what, the why, and the how behind containers and orchestration, being Kubernetes specific. And we'll tackle two individual topics during this session. One specifically focused on building Docker containers and how to build and run software within a Docker container. And second section of this session is going to be focused on running that container at scale within a Kubernetes environment. We'll close off the session with a very quick look into an end-to-end DevOps process within Kubernetes. But for more information there, we'll refer you to some additional resources. And that's what we'll tackle today. As a quick introduction about myself, as I said, my name is Nils. I work as a cloud solution architect at Microsoft, and my main focus recently has been around containers and Kubernetes and DevOps, and I'm working with a number of Microsoft strategic customers in helping them either migrate existing applications into containers and Kubernetes on Azure, or to build completely new platforms using those technologies. Based on my experience, I had the pleasure of co-authoring a book in the beginning of this year titled Hands-on Kubernetes on Azure, where I guide you through the how you can build Kubernetes-based applications on the Azure platform. And I blog about weekly on my own personal blog, where I share things that I've been working on, either for my own personal development or work that I'm doing with customers and just sharing what I'm working on. And on the personal side, I have a couple of hobbies which are not all compatible, but I like playing board games, I like beer tasting and trail running here in the San Jose area where I live. The beer tasting and trail running typically don't go very well together, so I try to keep them separate, but it's just fun hobbies to have. And with that, let's dive into the first topic around Docker containers and specifically where they fit in. And if we think about the evolution in software development that happened over time, we had existing applications that were moved to the cloud as either as virtual machines or containers, and more modern technologies like continuous integration and continuous delivery were baked into those applications. But to really gain benefit from modern infrastructure and cloud specifically, you need to re-architect those applications for scale and to make benefit of all of the cloud capabilities. And we're seeing an adoption in a lot of customers where as part of their application re-architecture and application modernization, they're adopting a microservices approach where they're pulling off or creating new services, not as part of a single monolithic application, but developing them as standalone individual microservices. And very frequently, containers are used to house those individual microservices. But let's start our discussion with looking into what a container is and what the problem is that containers solve for you. And to start off with, I won't start with a technical discussion. I actually start off with identifying the problem that containers are trying to solve. Because if we look in 2020 into our distributed application landscape, we are in a situation where we have multiple application stacks that are running in parallel, where we have just multiple different services and multiple different applications, potentially even with multiple different versions of certain background software that we're using. And if you check here on this slide, I even have an example on here where I have some background workers leveraging Python 3.0, and I have an API front end leveraging Python 2.7. And those two run in parallel, and they also run on multiple hardware environments, going from a developer's laptop to an on-prem data center, to public cloud, to production environments, to even container clusters. And we're ending up in a situation where we need to configure all of those environments to be able to support all of our applications and to make sure that whatever environment we end up with, we have the right version of the right supporting services. And this creates a sort of matrix from hell, where we need to make sure that each of the environments has the right supporting software to be able to support all of the applications that we need to or want to run. And if you think about the solution for this, the term container is borrowed from the shipping container ecosystem, where before the shipping container was introduced, I believe in the 1960s, shipping multiple different items on a ship was also creating a sort of matrix from hell, because you needed different equipment to deal with crates, then to deal with cars, then to deal with oil or other raw resources. And the introduction of the shipping container actually created a singular shipping format that could be used for different resources. So you could put crates and cars and barrels of oil all in the same container, and you had a single ecosystem of transportation and storage mechanisms that could be used to either transport or store those containers. And that helped with just handling shipping, and that has drastically improved the productivity of the shipping industry, as well as been able to lower costs, because that container has become like the default mode of the default modality to ship goods internationally. And that term container has now also been applied to our distributed applications, where rather than having to install supporting backend software on all of our hardware environments, let it be a development VM, a QA server, or your own data center, a container allows you to package your application or your specific service together with all of its dependencies into a single, let's call it packaged environment that can be run everywhere where there is a container runtime to run it. So if we think back of our example where we had an application that had Python 3.0 as a runtime requirement, and the second application requiring Python 2.7, each application could be put into a container with its requirements. So the one requiring Python 3.0 could be packaged with Python 3.0. The one requiring Python 2.7 could be packaged with Python 2.7, all within that self-contained Docker container. And then wherever that application runs, the only requirement is to have a container runtime or a Docker runtime. And those applications will run with their dependencies. And so that matrix from hell that we were talking about earlier becomes really easy to solve, because every application is packaged with its own dependencies. And that makes for a fact that wherever we have a Docker runtime, we can run or deploy that specific application. And so if we look a little bit under the covers of containers, containers are very frequently compared to virtual machines. And I sort of like that comparison, because if you just look at from a very high level perspective, a container is a packaging mechanism where you can package an application together with its binaries and any libraries that it requires. And the only thing it requires to run is the Docker layer so that the application itself can run. If you compare that to a virtual machine, in a virtual machine, you can also package an application together with its binaries and its libraries together, but you also need to package in the guest operating system. And operating systems typically are relatively, let's say, sizable, which makes for the fact that deploying a virtual machine, one, takes more time, and two, is a much larger unit of deployment as compared to a container. Depending on which software is running in your container, containers typically start up within a matter of seconds. And if you compare that to virtual machines can take multiple tens of seconds, if not minutes, to completely start up and be available. And copying a virtual machine from one machine to another also is much more of a heavyweight lifting experience that's required, because containers can be as small as a couple of megabytes or a couple tens of megabytes, depending on the application itself. Whereas virtual machines are much more heavyweight and typically are in the range of gigabytes in terms of their size. Now, if we think about those containers, to build a container, we leverage something called a Dockerfile. And things will become a lot more clear in the demo that I will show in a second. But if we think about the Dockerfile, the Dockerfile is a set of instructions that we give to Docker, where we tell Docker what it has to do in order to build our application. And what I show here on the slide is actually the Dockerfile of the demo that we'll be running in a second. But as you can see here, what we're telling Docker to do in this Dockerfile is we're telling Docker that for our specific container that we want to run, we tell it to start from a certain base, and I'll explain a little bit more what those bases are. I just label it as I am the one who's maintaining this. I'm then running a couple of commands. And essentially what I'm doing here is I'm installing 3 pieces of software. I am downloading another binary called Hey that I'm using to do some HTTP testing. I copy a script from my local machine into my container. I make that script executable, and then I simply tell Docker, every time you start this container, the entry point for this application is for you to just run that script that I told you to run. And what happens when Docker starts building this container is the container will start off from its base, which you see here, which is that Alpine 3.12.0. And then every step that I run in this process will add something called a layer to my Docker container. And then finally, the final layer with the entry point will tell Docker what to start when we're actually running this container. Now, when this script or this Docker file is executed, Docker will create something called an image. And those Docker images are initially stored on your local machine or your local development station, where you can very quickly run or start creating containers based off those images. But once you want to port your Docker-based applications to, let's say, a production environment or share them with other people, you use something called a image registry, where in an image registry is a place where you as a developer can push your images into a registry so other people can start using them. And then the people or the processes actually running your container in production will pull the image from the registry and then start running them wherever they want to run them. So that's a brief introduction into Docker containers. And to actually show you what we're doing, I will actually show you a small demo that I built to actually run this environment. So let me share my terminal here and show you what as I discussed before, I have a script here locally that's called sendEvent.sh. And what this script does is this script, I use that to test some scaling actions against an Azure Event Hub. And if I were to execute this script, it'll take about 5-6 seconds to return the first output. But what you'll see in a couple of seconds is a latency distribution against my 5,000 messages that I'm sending to Azure Event Hub. But what you see here is that I'm able to send about, let's call it 600 requests per second into my Azure Event Hub. And I now want to show you the same thing in a Docker container. So what I have here is I have my Dockerfile that I showed you in the PowerPoint slide. And this is exactly the same Dockerfile that I showed you in the slides. And I can now tell Docker locally to go ahead and build me a container image based on this Dockerfile. So I can tell it Docker build, and I just pointed to my local directory. That's why you see the dot. And then I will tag this image. And the reason I'm tagging the image is to be able to let's say very quickly be able to identify which image I want to run. And I can just call this, let's call this scale test as an example. And then when I execute this, you'll see that Docker very quickly goes through all the different steps where it's pulling the image from Alpine, it's then labeling this, it's running all the different commands, and then as the entry point, it's looking into my script. So if I now want to execute this, I can go ahead and do Docker run, and I can just say scale test, and this will run the script now no longer from just my local terminal, but it'll run it within a Docker container on my local laptop. So if I hit the enter button, again, we'll have to give it a couple of seconds to give me the first output. But once it gives me the output, you'll see that I'm getting roughly the same performance as before, actually a little better, but that's just dependent on the environment. But you see that I'm running the exact same script, now no longer on my local station, but I'm running that within the context of a Docker container. Now, let me exit out of this environment. Come on. OK. So the next step, if you remember from the slides, I now have this Docker image available on my local machine. The next step is to be able to get this container and push this into a container registry so it can be used by other applications or other people. And to do this, there's essentially two steps that I will have to take. One is, the first thing I'll have to do is I'll have to re-tag this image with a tag that contains the name of a Docker registry. And I already created a Docker registry before. So let me just run this command. So I will do a Docker tag on my scale test latest image that we just created. And I will tag this with the name of my container registry that I created on Azure. And I can then call this scale test again. And instead of latest, let's just call this live demo. And now we tagged this image with live demo. So if we now were to have a look into all our Docker images and look for our scale test images, we'll see that we have this same image, because you'll see that you have the same hash of the image itself, but we have it once tagged as scale test and once tagged as the image with the actual registry. And to push the image into the registry, I can run the command docker push and then call it the full image name. So this.azurecr.io/scale test live demo. And then once we're pushing this, you can see that everything is getting pushed. And we now have this container image available in our Docker registry. So if I were to show you this in the Azure portal, let me pull that up for you. This is that same container registry that I showed you in the demo. If we go into repositories now, you will see that we have our scale test repository right here. And we will see that we have the tag live demo that was created at 10:22 PST, which is the time that we are actually running this demo. And so to bring this back to what we were discussing, what we've done in this demo is we've created a new Docker image. We've been able to run that locally on my machine. And then afterwards, we've pushed that image into a container registry so that it can be used by other applications or other people to run themselves as well. And so the next step typically in a container environment is to deploy those onto a Kubernetes cluster for scale. But let's first think about why we would need Kubernetes to run applications, because what we've done up to now is we've ran one container on one virtual machine, and actually that virtual machine was my own laptop, but we've just ran one container on one machine. And some difficulties start to come up when you start thinking about running, let's say, 10 containers on one machine. You could just do Docker run like we did 10 times, and we can then run 10 containers. That's certainly possible. But what about running 100 containers across 10 virtual machines? That's where things start to get a little bit more complicated. And if you think about the issue with standalone containers, there's a number of things that can go wrong within a container environment. And what I have right here on this slide is just a quick example of a container environment where we have multiple instances of certain containers running on multiple machines. And a couple of things can go wrong. First thing that could go wrong is we could have a machine crash. And once the machine crashes, we will need some way to have container 1 and container 3 restart on either the same machine or on a different machine. Something else that could happen is one of our machines could be out of resources, and it could be consuming, for instance, 100% of its CPU. And we might need to do some sort of load balancing of our containers to different machines. Something else that could go wrong is we could have an application crash within the container. And if we're experiencing a application crash, we'll need for some mechanism to automatically restart that container and to do error logging. And so what Kubernetes does, and where Kubernetes comes into the picture, is Kubernetes is what we call a container orchestrator. And an orchestrator does a number of things in the container world. And if we let the slide complete, you will see a number of things that a container orchestrator can help you with. The first thing it can help with is the actual scheduling of the containers, where on the previous slide, we saw that one of the machines was out of resources, and the orchestrator could just help in scheduling containers on the right machine in our cluster so that we avoid those situations. Second thing it helps with is affinity or anti-affinity, where we want to either house certain containers on the same host or don't want two containers to be housed on the same host, which is affinity and anti-affinity. Orchestrators can also help with health monitoring of the nodes and the containers running on those hosts, as well as doing some sort of automatic failover in terms of health events. An orchestrator, such as Kubernetes, also helps with scaling and potentially doing auto-scaling. It helps with networking, making sure that containers running on different machines can communicate to other containers running on different machines. It can also help with service discovery or resolving names to IP addresses, so different applications can communicate to other applications. And finally, a container orchestrator, such as Kubernetes, can help in coordinating application upgrades. The reason why it can help is it combines elements of scheduling together with upgrades to make sure that if I want to upgrade an application from version 1 to version 2, that we can either implement a rolling update or a blue-green deployment or a canary deployment, and container orchestrators can very much help in doing those application upgrades. And so we've been talking about Kubernetes so far. So let's have a quick look in how Kubernetes works, and let's first look into how Kubernetes works internally. And I realize that there's a bit much details on this slide, but it definitely helps to wrap your head around what things are and what the different nomenclature is. And in the following slide, we'll actually discuss what things look like for a end user of a Kubernetes cluster. And if we think about a Kubernetes cluster, each Kubernetes cluster makes something available through an API server, and each request that happens against the Kubernetes cluster gets stored into a database running the etcd software, but that's let's say an implementation detail. But every request you make against Kubernetes gets stored in a database, and we then have a couple of elements running on master nodes or on controller nodes that manage either a scheduler and controller managers to make sure that the required workloads run on the required worker nodes in our cluster. And if you think about those clusters, we run the actual workload on Kubernetes gets deployed into worker nodes, and the worker nodes communicate to the control plane or to the API server through a piece of software called the kubelet. And the kubelet is responsible for taking instructions from the API server and actually running the workload on those worker nodes. And if you think about what this means in terms of the worker nodes, there's two things that happen when a container gets scheduled on a Kubernetes worker node. The first thing that happens is the kubelet will actually start the container itself and start running the actual workload. And the second thing that happens is a piece of software called kubeproxy will configure the networking on the worker node to make sure that all of the necessary communication that needs to flow either from the internet or between different worker nodes can actually flow within our cluster. And if we take this picture and we think about it from a user's perspective, if a user wants to start a workload on a Kubernetes cluster, the first thing that happens are step 1 and 2 on this picture, where the user does the same thing that we did earlier. The user has a Docker image and pushes that image into a container registry. The registry here is called out as Docker Hub. In our example, this was the Azure Container Registry. But the first thing that needs to be done is we need to have an image available that our Kubernetes cluster can pull from. And then the third step here is the user executes a command. There's multiple different ways that this can be done, but the example we're using here is kubectl run. where the user tells Kubernetes to run a certain application based on the image that was pushed into the container registry. Now, what then happens in essentially in the background, so the last thing the user does is step number 3, and then a couple of things happen in the background. The first thing is the piece of software called kubectl or kubectl or kubecontrol, whatever we want to pronounce this as. I'll just call it kubectl. Kubectl issues a REST call against the API server running on the master node. The master node will, as we discussed earlier, store that request in a database within the master nodes. And once that request is saved, this will trigger the scheduler within our Kubernetes cluster to actually go ahead and look at the definition of the workload that we want to run, and then go ahead and notify the kubelet on one of the nodes within our cluster to go ahead and actually run our container. The kubelet will then instruct the Docker runtime to actually go ahead and run a container based off our container image, and this will then finally pull the image from the Docker hub and run it on our node in our cluster. And this is how Kubernetes works from, let's say, a user perspective. And if we then think about what Kubernetes means on Azure, Kubernetes itself is, let's say, portable, extensible, and self-healing. Those are the aspects of Kubernetes itself as a piece of software. And what, from an Azure perspective, gets added to these capabilities is Azure makes it really easy to manage and operate Kubernetes clusters at scale, which will then enable you as a user of Kubernetes clusters on the Azure platform to accelerate your actual application development, because you no longer need to worry about the difficulties about setting up your cluster. You can create a cluster, and I'll show this to you in a second, in a matter of literal seconds, in just AZ AKS create to create a cluster, and you can really focus on your application itself. From a security perspective, Microsoft takes security super serious, and there's a number of security best practices that are implemented in the Azure Kubernetes service. And we also make a number of additional enterprise-grade security capabilities available to you as a user to further protect your specific cluster and the workloads that are running on your cluster. And essentially, Kubernetes on Azure enables you to run your workloads anywhere. And I don't want to go in detail on those capabilities here, but we have a service called Azure Arc that enables you to connect Kubernetes clusters running anywhere, let it be in your own data center or on other clouds, to the same Kubernetes on Azure infrastructure. So you can use the same policies and the same level of control and visibility that you're used to on Azure on clusters running anywhere. But if we talk about the management and ease of running Kubernetes on Azure, if you set up your own Kubernetes cluster, there's a whole lot of responsibilities that you as a customer need to take on. And part of the things that you as a customer have to do when setting up your own Kubernetes cluster is you'll have to configure your master nodes, and you'll have to set up the API server, the etcd store, the scheduler, controller managers, ways to communicate with your cloud provider. And all of that is quite a bit of work to set up. And what the Azure Kubernetes service provides you is we provide you with a fully managed Azure control plane where you no longer need to worry about both setting up, managing, and monitoring your Kubernetes master servers. All of that is managed from an Azure perspective. And the only thing you have to do is you can still deploy your applications against the Kubernetes API endpoint, and the Azure Kubernetes managed control plane will then go ahead and schedule the actual workloads to run on your virtual machines. The good thing about this service is that those machines, or the place where you run the actual workloads, is fully controlled by you as a customer. So you see the virtual machines that get created by the Azure Kubernetes service. You can join them to your own network, which means that it's very easy to integrate those clusters into any other applications or infrastructure that you have defined and that you are running. And to create a cluster, there's a couple of simple commands that you can run to go ahead and either create a cluster, upgrade a cluster, or scale a cluster. And all of that is pretty much abstracted away for you, where there's a couple of simple commands that you can run, either using the Azure CLI or using Terraform or using ARM templates, so that creating, upgrading, scaling, and managing your clusters is fairly easy and straightforward. And now let's go ahead and take the Docker container that we created earlier and go ahead and look into what this looks like if we were to run this on Kubernetes at scale. So I will switch back to our terminal here, and let me actually switch to the Azure portal first and show you I have a number of Kubernetes clusters running already, and I'm actually using this one titled core dump to run our workloads. And if you look at this cluster, it's called core dump. And if I were to do kubectl cluster info, if I would not make any typos, you can see that I'm running against this very same cluster. And the piece of software that we're using here to communicate with our cluster is called kubectl. kubectl is a client-side tool that is used to communicate with the Kubernetes API server, and that is used to create and view any workloads that are running. And if I were to go ahead and check which pods I have running on my cluster, I just have something running called the init node, which is another project that I'm working on. But we don't have anything running yet that is pushing our events. And if we were to want to create this, we would use something called, or we would use a file that contains our workload definition. And I already created a file earlier called deploy.yaml that we will make a very quick edit in. So this file is the workload definition that contains, or that will instruct Kubernetes on what to do. And what you see here is we are creating something called a deployment in Kubernetes. We're giving it some metadata, and we then provide the specification of our workload. We're telling it we want to run one replica, and we'll scale this up in a second to run more than one replica. And we're providing it some configuration data. And finally, we're telling it which container to run. And here we see that we're pulling in an image called push event reactor, which is what I tried yesterday during my demo. But we renamed our image to, if I believe, to scale test live demo. Let's just quickly confirm what we called it by going back to our container registry, because I don't want to make any mistakes in the demo. But if we go to our repositories, we see we have scale test, and it's called scale test live demo. So if I didn't make any mistakes, this should be able to work. So we can then write this file to our local disk. And we can then go ahead and tell Kubernetes to create this workload by running the command kubectl create -f, pointing it to a file, and by pointing it to our deployment.yaml file. And so now our deployment is created, and we can then go ahead and get a look at the pods that are running. And you see our push deployment is now running as a container on our Kubernetes cluster. And so I could go ahead and actually look at the logs of this single container. So I could do kubectl logs, push deployment, 748 tcpf, and J. And these are the logs of the container that's running. And you see here, I'm actually getting about 1,000 requests a second, which is pretty spectacular, which is better than I was getting on my own machine. And I'm getting those results fairly consistently. What I actually wanted to achieve with this container, and I think I mentioned this in the beginning, is I'm using this container to do certain skill tests against an Azure Event Hub environment. So let me show you the Event Hub that I have, and then show you the impact of being able to run multiple containers in parallel. So if we check this Event Hub, we can see that it's now provisioned for 1 throughput unit. But we have it configured to be able to auto-inflate throughput units up to 20. And that's what I want to go ahead and be able to trigger now, because I would like for my Event Hub to auto-scale. And to be able to configure this, or not to configure this, but to be able to trigger scale actions, I will have to have my container deployment run more than one container. And there's multiple ways in which we could do this in Kubernetes, but let me show you just one way this can be done. So if we take our deployment file from earlier, instead of here having just one replica running in the container, I can very easily change this 1 to 10, write this configuration back to disk, and then do kubectl apply of this deployment file. And very quickly, if I execute this deployment, Kubernetes will have taken this command. And if I again do kubectl get pods, we can see that we now, instead of one container, we very quickly have 10 different environments of this single container running. And even more, in my cluster, I have multiple nodes in this cluster. So if I were to do kubectl get nodes, you can see that I have 2 different virtual machines in my cluster. And if I were to show you those same pods or containers again, you can see that my containers are spread pretty equally between either the machine ending in a letter N or the machine ending in a letter O, so that my workload is spread out between the different machines that I have in my cluster. Now, the one thing that I wanted to achieve is to trigger the actual scale event on my Event Hub, and it takes a couple of let's say minutes for this to actually trigger. But if we go back into our Event Hub and we look into the monitoring for, let's say, the last 30 minutes, we can see that here is where we were doing the earlier work, where I was running the script either locally on my own machine or locally as a Docker container. And here is where we started doing the work against the Kubernetes cluster, where we were sending, with a single container on my cluster, we were sending about 52,000 events a second. where now we're already at about 220,000. No, we're at 80,000 events per second. And I actually hope that I can show you that, as you can see, we started off the demo with one throughput unit configured. We're now already at 3 throughput units that are configured. So this just shows you how easy it is to, from our Kubernetes environment, create a lot of scale against this this event hub namespace by very quickly creating containers and scaling from 1 to 10 very quickly. And that's a very quick demo about running containers at scale in Kubernetes. And to wrap this up, before we go into the Q&A, I wanted to bring this all together and show you what all of this would look like in a in an end-to-end pipeline. Because what we've been running so far is I've shown you what it looks like to run Kubernetes on, let's say, on my machine, or to run a container on my machine, and then use my command line to connect to a Kubernetes cluster, which is really good for testing and development, but which doesn't scale or isn't the best way to approach things for a production environment. So if we think about what this looks like, we would still have a developer run their inner loop development locally and interact with an Azure Container Registry to pull in certain base images. But if we think about a end-to-end DevOps pipeline for this, rather than the developer pushing new containers into the registry and then interacting with a Kubernetes cluster, what typically happens in a DevOps pipeline is you would then have that developer push their updated code into a source control system. Let that be Azure DevOps, let that be Bitbucket, let that be GitHub. Just push your code into a source control system, which will then trigger a build phase or a phase of continuous integration and continuous testing. And the output of that build phase is our build Docker image, which we will then push into the Azure Container Registry. And I hope you here already see the difference, where what I showed you is I showed you how I did this from my own machine. But typically in a production environment, you don't have the developer pushing images into a registry. You would have your build system be pushing those images into the registry. And once the image is built, you would have a continuous deployment process that would take those container images that were built and push those into your production environment, so that you have an end-to-end pipeline to take the container images that were built, push them into your production environment, and then finish this off with monitoring the workload at scale, and then providing that monitoring feedback back to the developer to work on new functionality. So this is just a view of what this would mean in a DevOps pipeline. And if you would want to learn more, I have 2 resources at the end of this slide here that can provide you some more information if you want to learn more about containers and particularly Kubernetes on Azure. The first one is the book that I mentioned at the beginning of this presentation called Hands-on Kubernetes on Azure. That is available as a free download at the link you can see here on the slide. And it's a book with 11 chapters filled with hands-on examples that you can use to really learn what it means to run applications on Kubernetes on Azure. A second link I have here is we do have a guided learning path on a system called Microsoft Learn. That is also a free resource that you can access using the link you see here on the slide. And that guiding learning path is a really good way to get started with Kubernetes. It contains a number of just learning environments, as well as a couple of demos that you can run to just learn about Kubernetes and what that means. And that is the end of the presentation itself. I will now quickly have a look at the Q&A that we went through during the session and see if there's a couple of questions that I can tackle live here at the end. So let me pull up the Q&A and see which questions came up. So a first question we have was, does Docker container have any file system? Example, NTFS or FAT? That is a really good question, and the answer is yes. Docker does have a file system, and depending on which operating system that you're building your Docker containers for, let that be for Windows or Linux, because Docker works for both Windows and Linux. You would just have the default file system from that operating system, typically NTFS for Windows or ext4 for Linux, be applied to the Docker container. Important side remark is containers themselves are typically ephemeral resources where a container can very quickly be created, but also very quickly be destroyed. So if you're thinking about files in containers, the default advice you'll get is to not store files that are required in your container itself, but to store certain files. Let's say we're running a database in a container. You would store your database files on an external storage. Let that either be a disk that is attached to the container or a network share that's attached to the container, so that if the container were to be deleted, you still have access to those files. So that's an answer to that question. Second question is, can we get the PowerPoint presentation? I will work with the event organizers to share the slides themselves, so I'll make those available. And another question is, any example of affinity and anti-affinity? So the best example I can give about affinity is if you have an application that requires the front end and back end system to be hosted on the same node to be able to get very high performance because they communicate a lot with each other. That's an example of affinity. An example of anti-affinity is, let's say you have two workloads on your cluster that are both I don't know. Okay, so I just got an error from Teams, so I'll retract a little bit on what I was just saying. So an example of anti-affinity would be if you have two workloads that both are very CPU intensive. You could put an anti-affinity rule in place so that those two workloads are never scheduled on the same node, so that they can both benefit from all the CPU available on the nodes they are scheduled on. Another question was, what is the difference between the kubelet and kubeproxy, and are both communicating to the container? And that's an excellent question. So the difference between the kubelet and kubeproxy is that the kubelet itself is responsible for scheduling your container and actually starting your container on the node that it should be running on. And kubeproxy is responsible for configuring the network on that host, so that if there's any connectivity requirements for your container, that the right ports are opened on the machine to allow network traffic into those containers. Next question, whatever we are writing under the containers in the deployment.yaml file, question whether these images should be available in the Docker container. So I'm not sure I understand the question, but the main, how I understand the question if I show you that deployment file again, what's important here is the reference to this image, and this image has to be available for your Kubernetes cluster to be able to run the application. Because if the Kubernetes cluster cannot get to the container image, it won't be able to actually run the workload, and it'll give you an error that it cannot fetch the image. Can you please speak to how Azure differentiates itself in terms of container management and diagnostics? We have been considering AWS, but are open to Azure. That's an excellent question, and I'm not sure about the AWS positioning, but in terms of container management and diagnostics, we do have a number of integrations into the Azure Kubernetes service that make it really easy to manage and monitor your deployments. I don't want to go too much in depth here, but let me just show you one example. If I were to go to our Kubernetes cluster that we were running earlier, we are trying to make it as easy as possible for you to monitor your workload. And for instance, if we were to go into the workloads tab on in the Kubernetes in the Kubernetes view in the Azure portal, you can see here that we have our push deployment showing up here, and we can see a lot of the details about our workload here. We can see when it was created. We can open up the pods themselves, get information about them, get any events that are linked to that pod. So I think that's one area that we're focusing on. Second area is just making all of the integrations into different Azure services and open source services as seamless as possible. We have Azure Monitor for containers to monitor workloads. There's a number of integrations into Key Vault, into functions. So that's where we're definitely innovating and trying to stay ahead. Scrolling down. How do you manage binaries in a Docker image? If you have built your application, for example, with Python binaries and there is a vulnerability, do you need to recreate a completely new image? Or can you update the image with the latest binaries, assuming the application can run on both versions of Python? Carlo, that is an excellent question. And typically what you do in that case is you would build a completely new image with the latest binaries. The reason you would build a new image is if you think about your Kubernetes environment, pods or containers can be very easily deleted and recreated, and all of that is very dynamic. And if you were to go into a container and update only that individual container, that state would not be persisted, because as you can see, I have 10 running right now. If I were to update this to 11, that 11th container would not be updated. So you would definitely update your container image. And typically when it comes to vulnerability scanning, there's a number of tools such as the Azure Defender for Azure Kubernetes and the Azure Defender for Azure Container Registry that can help you identify any vulnerabilities in your container images. And you would typically create a feedback loop from those alerts into your DevOps pipeline that I showed earlier, and use that to build those new images and make sure that you have updated images available. Could you share the links, please? Yes, the links will be shared, and I'll post them on the meetup page. Is there any repo for your sample? No, I don't have a repo for this right now, but I'll try to remember to create it on GitHub and share that on the meetup page for this event. Are containers superior or inferior to VMs? I would say that containers solve a different problem from virtual machines, and I wouldn't say that either one is superior or inferior. I'd say that containers solve the application packaging and application delivery question of deploying a workload into production, whereas virtual machines are great to run containers. So you can run multiple containers in a virtual machine, and the virtual machine contains the operating system. So both are not superior or inferior one from another. It's just different goals that they address. And then the final questions. Kubernetes clusters provided by Azure are managed by Azure. In that case, other than app deployments, what other tasks a cloud engineer is expected to do to support production environments which are hosted on Azure? Excellent question. So typically there's two roles that you see in customers that are running applications on Kubernetes on Azure. One is the application operator, and the application operator typically just creates the containers and creates the necessary YAML files to run them on the cluster. In terms of platform, that's the second responsibility is more of the supporting of the platform. There are still a number of tasks that you as a platform operator are responsible for when running applications on Kubernetes on Azure. I think the most important ones would be keeping your cluster up to date. From an Azure perspective, we make new versions of Kubernetes available on AKS frequently, but we do not automatically apply those to your environment to make sure that we don't break your running systems. So as a cluster operator, you still have to regularly, let's say, every couple of months, or even sooner if possible, go into your environment and verify and that you're running on the right version, because Kubernetes evolves really quickly and there's new releases of upstream Kubernetes every 3 months. So that's one task. Second task is monitoring scale of your cluster. We have capabilities to do auto scaling of your cluster, but you as an operator still have to configure the auto scaling itself. And then a third task would be related to security, I would say. Although we do secure the platform itself, we also make a couple of security solutions available for you to run and install on your cluster. So there's a sort of shared responsibility model between you as a customer and Microsoft when it comes to operating those Kubernetes clusters. And I am going to stop the event here because we're already 5 minutes over, and I have to run to some other meetings. But I do want to thank everybody today for joining. The recording of this event will be available on YouTube later on as well. And I will make sure to share the slides and to share the links that were shown in the slides later today on the meetup page from the Microsoft Reactor. And with that, thanks again, everybody, for joining. And if you want to stay up to date with what I'm doing, I put my Twitter handle here on the slide, so feel free to follow me on Twitter and have a nice rest of your day. Thank you, everybody.